First of all, thank you for the invitation. It's a pleasure to be here. And this is the title of my talk, and it's a big, big topic, and I won't be able to cover all aspects of it, but with any luck at all, I will be able to cover aspects of it that bear directly upon some of the things that David just introduced, in particular about the heat gain. But also something else that's of great importance in the ocean plays a big role in, and that is the hydrological cycle of the planet. I'll start off by reiterating a couple of things that were just mentioned. This is from the IPCC report, the most recent published report. This is the CO2 record. It was presented in the previous talk, and it shows some very important things, and I'll reiterate them. Basically, for the last 600,000 years or so, the newest records go back 600,000 years, the CO2 concentration of the atmosphere has never been much above 280 ppm. There was a spike here and there, a little bit higher than that, but never been above 280 ppm. In fact, using other proxy records, it's difficult to find values higher than 280 parts per million, even on several million-year time scales ago. You have to go back to earlier parts of Earth history to find atmospheric CO2 concentrations that high. The other thing that's really important to point out is the rate of change is really rapid and not been seen before in the geological record as it's been measured, at least so far. And the third thing, to reiterate, is that there are only a few ways that you can change the planet's temperature on a whole. You have to disrupt its energy balance somehow. The sun can change its intensity. That's one way. The Earth can change its reflection by land use policies, things like that. You can have more forests or less forests, and all those things, more ice and less ice. That all changes the amount of energy that's reflected immediately back out to space. Or you can change the greenhouse gas content of the atmosphere. The fact that the greenhouse gases are going up this fast and this high means that the Earth is receiving and keeping more energy in its climate system now than it was 200 years ago. That's a straightforward fact. The difficult issue is to determine where that energy is going once it gets into the climate system. This is the figure from the IPCC report that shows the average temperatures for the Earth over the last 1,000 years. As was pointed out before, some of it is from direct measurements using instruments that go back about 150 years. Others of it are from geological proxies. But what we see here is that up until about 2000 or so, which is about the published date of this record, only just at that time were mean temperatures of the planet starting to exceed the background variability and uncertainty of what the geologic records were. The issue here is that this is a measurement of the atmosphere only. It's only one component of the climate system. And one of the reasons that this rise in temperature has been as small as it is reflected here is because the oceans exist. And that's why the oceans are important to this problem. So I'm going to step back. When I was in college, and every college I've ever visited has had an introductory oceanography course for non-majors that sometimes might be referred to as, in a derogatory way, of course, notions of oceans or our friendly ocean or something like that. Okay? It's your basic aspects of how the ocean operates. I'm going to go through several important factoids here about the ocean and about the properties of seawater that I want you to know about before I get into the climate problem. Okay? The first and most important part, not the most important part overall, but a very important part, is that because the climate system is a system that captures energy from the sun and redistributes it, the ocean and the atmosphere are both involved. The energy is captured by heating of the surface of the Earth, and that heat is then transferred to other components, and in one important way, it's upward into the atmosphere. Now, the fact that the ocean covers 70% of the planet means that it is driving, to a great extent, the surface heating of the atmosphere and setting the patterns of atmospheric circulation. So the sheer aerial distribution of the oceans means that it is the largest factor in setting the patterns of how the the atmosphere is circulating. The ocean is big, and because of the properties of seawater, it stores 1,000 times more heat right now than the atmosphere does. So if you look for the heat on the surface of the planet, and you want to find it, you have to look in the oceans. The other thing that's important to know is that seawater is a more efficient storage medium for heat. It's 4 times more effective than the atmosphere. And what I'm going to show you is that there's been a significant heat gain in the oceans, which has tempered the amount of warming that's going on the planet so far for the last 150 years. The other thing about the oceans that's important in the climate system is that, as I said, the climate system is a redistributor of this energy that it's receiving from the sun, and it's being redistributed by 2 mechanisms. One is by how the ocean circulates, and one is by how the atmosphere circulates. Now, the atmosphere is the larger component in the climate system. Up to maybe 3/4 of all of the energy that is received at low latitudes that is transported towards the poles is being transported by the atmosphere. But somewhere between 25 and 50% is being transported by the oceans. Now, the interesting thing about the oceans is that it's not fast compared to the atmosphere. If you're a Weather Channel junkie like me, when I was planning this trip out here, I saw that there was a low-pressure system that was developing in, it's called an Alberta Clipper, southern Canada, northern western U.S. And I mentioned that it looked like I might not be able to get out of Boston on Thursday. Now, I saw this on Monday, and the reason that I was worried about it is because I knew that this thing would only take a couple of days to go all the way across North America. The atmosphere is fast. Now, the ocean has similar disturbances in the way it circulates, but a disturbance that was at the same geographic position in the oceans, traveling that same distance, could take as much as a couple of years to move that distance. It's a significantly slower acting fluid on the planet. So when you talk about changes that have gone on in the oceans and when you might see their effects, you have to think about them farther in the future. That's an important thing. I'm a geologist by training, and it's easy for me to think about early Earth and long time periods and things like that. I find that when I talk to a lot of the general public, it's hard for them to think beyond the duration of a 30-year mortgage. That's about the longest length of time that anybody ever signs on to do anything. Okay? But what we're talking about with things in the ocean, I'll be describing to you a circulation process that takes 1,000 years to occur. And things that are happening this year in the North Atlantic will show up in the Pacific 1,000 years from now. Another important thing about the oceans is that in some locations, it's the major source of heat, and in others, it's not. And the North Atlantic tends to be one where it is the biggest source of heat being delivered to high latitudes. And because it's this surface interaction with the atmosphere is so important, the ocean is setting the long-term patterns of how the atmosphere is circulating. So, if you look at these 2 components of the climate system, another thing to keep in mind is that the atmosphere is above the surface, and it is flowing in this latitudinal belt from east to west of the trade winds, relatively unimpeded by the surface features of the Earth. The mountains aren't very high. They don't block the atmosphere. There's a large, what we would refer to as zonal circulation. The same sort of thing happening here in the westerly belt, where you're flowing from west to east. You know, the Rockies certainly play a role, but most of the atmosphere is flowing above the significant mountains. The oceans, on the other hand, are bounded by continents everywhere they go. And the net circulations in the oceans tend to have a lot of north-south component because of that. The ocean's being pushed around by the winds, but they run into these boundaries that force it to flow northward rather than having a straight east-west or west-east flow like the atmosphere does. Now, how will the oceans change as the Earth warms? Okay, here's a really simple one. The oceans are going to warm. And because of that, sea level will rise. I'm about to document how much warming has occurred for you. Here's another aspect that's really important. Its salinity balance will be altered. Now, the properties of the ocean waters that are important are its temperature and its salinity. These two properties together determine the density of the water, and the density of the water determines how the ocean circulates in its interactions with the wind field. So, if you change temperature, you change salinity, you change density of the ocean water, and that changes the way the ocean circulates. I'll spend a significant amount of time talking about how the salinity balance has changed. The ocean's also going to be reduced in its ability to absorb CO2. Right now, somewhere on the order of a third or so of the emitted fossil fuels that are burned each year actually are absorbed by the ocean and don't play a role in greenhouse warming. The other two-thirds do play some significant role in either enhanced biomass or increasing CO2 concentration of the atmosphere. And as the oceans warm, the solubility of CO2 in the oceans is going to go down, and that will mean that fossil fuel burning in a warmer ocean world will result in a net greater effect of CO2 on the atmosphere. And the other thing that's important is that as the Earth warms, the oceans are going to change, the surface heating will be different, and it will impact atmospheric circulation, storm tracks, the severity of storms, and the frequency and distribution of droughts. And that's because the surface distribution of the heating of the oceans controls the planet, controls where storms go, controls the evaporation and the precipitation. So places that are destined to be dry in the future are going to get significantly drier, and then locations that are destined to be wet are going to get significantly wetter. Higher temperatures at low latitudes might mean that hurricanes are of greater severity. You probably heard a lot about that last fall. These are important aspects of the climate that the ocean is going to play a major role in. All right, how about some data? Now, when we talk about knowing what the mean temperature of the Earth is in the atmosphere, the records do go back close to 150 years or so. When we talk about what happened in the oceans, the records go back about 50 years of inequality. And the reason for that is that was about the time when the Cold War began, and temperature and salinity control the sound velocity and the sound distribution in the oceans. And the major reason during the period from about 1950 to about 1990 that the oceans were actually even being measured for their temperature and salinity was so that we could hide our nuclear missile submarines and so that we could find the Russian nuclear missile submarines. It was really a defense-related phenomenon for this type of research and not a climate-related phenomenon. So to go back prior to about 1950, the data becomes incredibly sparse and far inferior. So almost everything that I show you about the history of the oceans from measurements by scientists is going to stop somewhere around 1950, and that's the reason for it. But if you compile the data for the last 50 years or so, as was done by Sid Levitas and published in the year 2000, what you see is that in the Atlantic Ocean, in the Pacific Ocean, in the Indian Ocean, and in the Southern Hemisphere, and cumulatively in the world oceans, over the upper 3,000 meters of the water column, the oceans have been becoming warmer. It hasn't been a monotonic change, just like the atmosphere hasn't been getting warmer monotonically, but it's definitely been getting warmer. What's different about the oceans is the scale. If you can read this scale, this is the temperature anomaly, and this is 0 and 0.04 degrees centigrade. So over the upper 3,000 meters, the amount of warming has been 0.04 of a degree centigrade, which is measurable accurately using these techniques. That's not a lot of temperature change, but it's a lot of heat gain because of the properties of the seawater. The net warming, on average, is about 0.06 degrees globally. The way that translates into an energy gain is that the oceans gained 18.2 times 10 to the 22nd joules, which is a measure of the energy gain, and the atmosphere gained 6.6 times 10 to the 21st joules, or the oceans gained 30 times more of the net energy that the Earth maintained because of higher CO2. So almost all of the net energy gain went into warming the oceans, even this small amount. Now, in all the models, this relationship is indistinguishable from the effect that you would expect from a rising CO2 due to anthropogenic sources. Okay? This is a really important fingerprint of global warming, that this is what you would expect to happen. Now, one of the things that you have to remember is that this, although it has kept the atmosphere from warming much more, the oceans won't be taking on a lot of heat forever and ever and ever without releasing it somehow. The oceans only capture heat, move it around, and release it. They don't actually create heat or anything like that. They don't destroy heat. But if the oceans continue to gain heat, as they change their circulation, this heat is likely to be released sometime into the future. Also, this net gain of energy right here relative to the atmospheres is one of the reasons why, even if you cut off all fossil fuel emissions now and stop raising the CO2 content of the atmosphere, the temperature of the planet would still continue to rise as this energy that's now in the oceans was slowly coming out and being sensed in the atmosphere. So it's important to take away from this that the oceans are an important part of this process, and what they are doing is mitigating the warming in a way that has made it smaller and will make it slower than would happen if you didn't have oceans on this planet. The other thing, and it was mentioned in the previous talk, is that warmer water is water that will expand. One of the basic properties of seawater is this expansion. And it has had a significant impact on sea level, will continue to have a significant impact on sea level, but in the future will be overtaken by the melting of glaciers and things like that, which will rise sea level due to the actual addition of more water into the oceans. So the effect will be to delay the warming of the atmosphere. And this is important to keep in mind. The rate and magnitude of future global warming will be affected by how the ocean circulates, when and where it will release what is now currently stored heat that you're not sensing in the atmosphere at this time. Now, the second property of seawater that's really important is this salinity. So I'm going to talk about salinity a little bit, and I'm going to step back into notions of oceans one more time to give you a few factoids before we move into the climatological impact. Not only do they cover 70% of the surface, but the oceans contain 97% of all water on the planet. It's a lot of water, okay? The atmosphere and the ocean work together to create the hydrological cycle that brings the lovely snowfalls that make Alta a great spot to ski. That water is derived from the oceans. Evaporation on the planet, 86% of all evaporation is occurring over the oceans. It's the major starting point for the sources of precipitation that we see in the ocean, in the climate system today. And about 78% of that falls back onto the oceans. The difference between 86% and 78% is the rainfall and snowfall that falls on land and becomes part of the continental hydrological system. These are big numbers. The numbers are so big that, to put it into context, if you increase Atlantic precipitation by just 1%, that's equal to the annual runoff of the Mississippi River. It's a huge amount. So small changes out over the oceans in terms of evaporation and precipitation are moving around tremendously large amounts of water. So they're a key element in the global water cycle. Now, what will happen as the Earth warms? The properties of water are such that as it warms, the vapor pressure goes way up, so that warmer water tends to evaporate more. So a warmer Earth and a warmer atmosphere will carry more water vapor. This is an exponential relationship of the vapor pressure as a function of temperature. This is going to enhance the hydrological cycle in ways that are very difficult to predict, and it's also going to change the salinity distribution in the oceans as we measure it. This figure shows two different things, but it links how the atmosphere, evaporation, precipitation affects the ocean's salinity. Salinity in the oceans, the total amount of salt is fixed over long periods of time. But the ocean and atmosphere are constantly evaporating and precipitating fresh water, so that you're taking fresh water away from this salt solution in some places and adding fresh water to this salt solution other places. On the right-hand side is a figure that shows in orange all of the locations where evaporation exceeds precipitation on an annual basis. So every location on there that's orange is a net source of water from the oceans into the atmosphere due to evaporation. Every location on here that's blue, evaporation is less than precipitation. So every location that's blue is a net receiver of rainfall due to enhanced precipitation over evaporation. You can see that most of the orange areas tend to be located in the oceanic latitudes equivalent to the major deserts of the world. It's because those are the locations on the planet where evaporation exceeds precipitation, both on the continents and the oceans. Now, the result is, over here in the oceans, if you map the salinity of the surface waters, what you'll see is that there's a really large, bright red bullseye there and there in the Atlantic. Those are the highest salinities observed in the surface today. And then moderately high salinities in the Pacific, north and south. They match up really well with these areas of evaporation. You'll notice that there's lower salinities at high latitudes where there's net precipitation, low salinity, net precipitation. So the salinity of the oceans is telling us what the precipitation and evaporation history has been to some extent by monitoring its salt content. I also want to point out one other thing. You'll notice that the Atlantic is saltier than the Pacific. And the reason for that is that the Atlantic is actually losing fresh water to the Pacific. So water is being picked up at low latitudes in the Atlantic, and it's taken by the winds, the trade winds, right across the Isthmus of Panama, which is not a blocker of the winds, and most of it rains out into the Pacific. So there is a net movement of fresh water from the Atlantic to the Pacific. Now, if that was occurring in and of itself, then the Atlantic would always be getting saltier and saltier and saltier. But it doesn't happen alone. What happens to compensate for that is that the Atlantic exports salty water through the oceans to the Pacific. And that fresh water that rained in the Pacific meets up with the salty water from the Atlantic. And I'll go into that in a minute. Now, these salinities are changing. And they're changing in a way that is yet another fingerprint of global warming. I'm going to focus on the Atlantic because some of the best data is there right now. And I'm going to show the salinity history along this line at 24 north. Right here is the maximum salinity in the North Atlantic, very, very high values. This is where maximum evaporation minus precipitation occurs, right along this line. And the history for the last 45 years approximately shows, this is a complicated figure, I apologize for that, but the most important thing are these red pluses. We lost the projector. but the computer's still working. Stop that clock, okay?
You didn't hit question accidentally.
Not that I know,
Not that you know.
but if you know how to do it, test it.
Well, I don't know if that. That's not it. Well, now I broke it even more.
You know, oh, sorry. If you have a question, I could actually take a question at this point. You know what I mean? Yeah.
Is that salty water near the Amazon? Maybe have something to do with
The
the
question was, does the salty water that's near the Amazon have anything to do with the current drought reported in that region? And I would say the answer to that is probably no. The timescales of those two things are probably very different. You know, that the Amazon drought is a much shorter timescale than the integration of the salt in this location. Okay.
One slide you showed on the warming of the oceans, about 85 to 90 years drop. It's not warming. Why was that?
Don't know the answer to that. That's it's a difficult question to know any of the small changes that are occurring on those timescales. Yes. Actually, I don't know the answer to that. The question was, how does the energy gain that were spoken about in terms of the borehole temperatures, I believe, compare to the energy balances that I pointed out for the atmosphere and the ocean? I don't know the answer to that question.
Henry Pollack has published a paper on that, and we've done a similar calculation. You get what Henry, the number.
The number is about the same as the atmosphere. It's
Okay.
order of magnitude smaller than the ocean.
Okay.
The upper part of the rock in the earth, because it's warm, is also storing a certain amount of heat, which will release.
Yes.
Does that show that more salinity means more evaporation? Is that right?
Higher salinity results from greater evaporation, yes.
But this is against the theory, it's Stegner.
It's against what theory?
Salinity reduces the amount of evaporation.
But the loss of the fresh water due to the evaporation is really the driving force for what's going on here. You're saying that saltier water evaporates less, but not that much less. I mean, the changes in salinity are small. Yes?
I saw a study that perhaps was just an hypothesis, that actually in the Arctic ice cap, because water expands into ice, and it's basically floating on the ocean, and as it melts, it'll actually rise the level of the ocean.
The effect of the melting of floating ice will not change the sea level significantly. Just like a cold drink and the ice melting doesn't change how things go in a cup. You know, there's not really much effect on sea level if it's truly floating. Now, a lot of the ice shelves in the Arctic are actually grounded a little bit, so they might have an effect on sea level. I'm going to try to continue here. I think I was at this point of saying, along this line, the highest salinities in the Atlantic, if you track the changes in salinity that have occurred for the last 40 years or so, you look at these red pluses, and what you will see is that salinity has been increasing And it's increased by about 0.03 parts per thousand. Now, the numbers are about 37 parts per thousand. So 0.3 out of about 37 is the increase in the surface salinity in that location today, or in the last 40 years. If you translate that into the amount of fresh water that had to be removed, it's this line right here. It's approximately an imbalance, an increasing imbalance of 5 centimeters of fresh water being removed by evaporation per year, resulting in approximately 200 centimeters or 2 meters of fresh water having been lost to the tropical Atlantic due to higher evaporation due to greenhouse warming. It's also expanded in its area. Okay, thank you. In the 1970 time frame, the highest salinities were located right about here in low latitudes at this yellow location. By about the 1980s, the early 1980s, the amount of high salinity water of the same value had expanded, and there was really high salinity water here off of the Amazon region. And then by the late 1990s, a significant geographic expansion and much higher salinities located at these locations. Significant change in evaporation that's occurred at low latitudes due to the warming of this water. Now that water has to go somewhere. Some of it's going into the Pacific, some of it's going into high latitude. It's almost all going to end up falling in some location where precipitation exceeds evaporation at some level. Those are going to be enhanced. Now I'm going to start talking about those locations here for a few minutes and then wrap this up. At high latitudes, as I showed before, there is enhanced precipitation over evaporation, which means that in general, the surface salinities are generally low. And in the Arctic, those low surface salinities sit on top of higher salinity water, and they create what's called a halocline, a density barrier that inhibits vertical mixing. And one of the consequences of that inhibition of vertical mixing is that sea ice is able to form each winter. And what we have been observing, and what Mark Serez will no doubt talk about later in his talk, is that the amount of sea ice in the Arctic has been relatively consistently decreasing for at least the last 20 or so years. For instance, in 1979, the map of the summer Arctic sea ice, so this would be the minimum extent of sea ice for that year, looked like this. And in 2000, it looked like that. So that's the geographical distribution of sea ice in the summer. I love doing this. PowerPoint's wonderful for this sort of thing. This is as close to an animation as I came for this talk. Okay? That's a big change in the amount of fresh water. When you melt the sea ice, you expose the fresher water to the possibilities of mixing by the winds in such a way that you may actually remove it from the location where sea ice can form again the following winter. So it's possible that by melting sea ices, you will be adding fresh water to the ocean in the locations below that density boundary that I spoke of, the halocline. The other thing that's happening at high latitudes in the North Atlantic that's really important is that Greenland is melting. And even recently, within like the last 2 or 3 weeks, there have been some really important publications suggesting that the rate of melting of Greenland has even maybe doubled in the last decade or so. That's a really significant finding. This is about a year old, this particular plot. And what you see here is Greenland. Now, Greenland holds about 7 meters of sea level equivalent. So if all of Greenland was to melt, sea level would rise by 7 meters. It's a significant amount of fresh water. It's melting every summer at elevations lower than this dotted line. So the central white portion right here is all higher elevation Greenland ice, which tends not to melt in the summers because it doesn't go below freezing. But every summer below these elevations, you tend to get a lot of melting. And that water is not hanging around and refreezing the following winter. It's draining through the ice sheet and flowing back into the oceans. And it's starting to have a significant effect on the salinities at high latitudes. And I'm going to finish up the talk with this summary of information. The salinity distribution for the last 5 decades is presented in this panel on the left here. 10 more minutes, thank you. What this is that oceanographers like to do cross-sections. This is a cross-section of the upper 1,000 meters along this red line right here. This is the Norwegian Greenland Sea. It is the location where fresh water is being exported from the Arctic. There's a net flow of fresh water from here to here. And this is the western side, and this is the eastern side. So along this transect right here, in 1950s, the salinities in the upper 1,000 meters were this light powder blue color, which is 34.9 to 34.95. Not a very important number for you to remember, but the change is what's important. In the 1960s, you started to see maybe a little bit of a change, but not much. But by the 1970s, and then the 1980s, and the 1990s, significant amounts of fresh water started to be measured along this cross-section. The changes are small, 34.9 to 34.8, a tenth of a PSU, small amounts. But the equivalent of a couple meters of additional fresh water having been added into that water column and diluted the whole water column. So it is possible, in fact, to start to balance where the loss of fresh water from the low latitudes due to evaporation is occurring and the gain of fresh water due to higher precipitation and melting is occurring. If you summarize the total amount of water that has been added in these locations in the North Atlantic for the last 50 years, it looks like this. Now, the Nordic storage anomaly is the Greenland Sea, which is this upper region right in here. Then I'm going to be referring to the subpolar region, which is down here as well. So the Nordic location was relatively flat, and then around 1967 or so started to gain fresh water. The subpolar basin actually was losing a little bit of fresh water and then rapidly gained it around 1970 and has continued to gain. And then the combined is this purple line, the sum of these two lines right here. And if you look at this, the total gain for the Nordics was 4,000 cubic kilometers. The total gain of fresh water was 15,000 cubic kilometers for the subpolar region. And the combined is 19,000 cubic kilometers. And it came in like this, with a rapid pulse right around 1970, which is reflected in this rapid change right here. So what this says, this figure says that overall, these subpolar basins have been gaining a lot of fresh water. Again, like other aspects of the climate system, it has not been a monotonic increase, but rather sudden change, with the largest change occurring around 1970, which has been traced to a large discharge of sea ice from the Arctic, which oceanographers have referred to as the Great Salinity Anomaly. Now, this is playing into the ocean circulation system in a very interesting way. The oceans are circulating in the largest scale like this, where warm water at the surface is flowing up into high latitude locations and cooling. And that cooling, as long as the water's still salty, means that the water sinks and flows as a deep current back toward the Pacific Ocean. And this is the circulation system that I said takes about 1,000 years. This is a long time scale problem. The reason that this is occurring is because each winter, the warm, salty waters from low latitude that flow up into this location are, in fact, warmer than the overlying atmosphere, and a significant amount of heat goes up into the atmosphere. That's the energy exchange between those two, which changes the density of the seawater, which causes it to sink and to flow southward at depth. Now, this is now the same type of figures I showed you for the salinity in the tropics, except it's the salinity at high latitudes. In the 1970 time frame, the deep waters at about 3,000 meters weren't very fresh. But around 1980 or so, you started to be taking up much fresher waters in the deep waters. And by the late 1990s, it was possible to trace all the way down to near Brazil the additional fresh water that's been coming in at those high latitude locations. Which means that fresh water is being taken up right up at this location and flowing along that broad arrow, and it's reached about this point in space. So the fact that we're adding fresh water to the North Atlantic region, which could have the effect of reducing the density, is not actually playing a role in reducing the density enough to stop this circulation system. That's an important thing to recognize. I'm going to skip this. The reason that that's important is that this is the pathway of these circulations. This is the surface current, which is warm and salty, and it's going to see a report. There were 9 models that attempted to figure out what would happen to the ocean circulation in the future as CO2 continues to rise, and they gave 9 different answers. This is 1950s to the 2000 time frame, and this is the perturbations that were recorded in that overturning circulation of the North Atlantic, and it's one of the biggest unknowns that we have. And the extent to which a change up in here could affect temperatures then is really not well predicted at this point in time. One thing I'll say is that if it was to happen in the near term, which is very unlikely, the region would get cooler. If it happens a century from now, the region would not get cooler than today, but the global warming that will happen due to the continued CO2 rise in the atmosphere would be mitigated in this location because of the cooling that might occur at that time. So I'm going to finish up with some more factoids just to bring this together. The ocean and the atmosphere work together. The surface conditions of the ocean set the circulation of the atmosphere, so what the ocean does is important. The deep water that's produced in the Atlantic is exported to the world, and it's density-driven. Warm, salty water becomes cold, dense, salty water, and that salinity balance could be changing right now due to the warming of the planet. The heat released to the atmosphere by the oceans is an important source to this location, this Atlantic region. Several models predict that this is going to change, and some of the changes predicted by the models may be occurring today, but so far they're only showing up in the changes in the heat content and the changes in the salinities, and not actually showing up in changes in the circulation yet. Thank you very much.